Okay, I want to move on now to talk about Chapter 6, where we're talking about the reactions of alkenes and the addition reactions. These reactions are essentially the opposite of the elimination reaction. So if you recall from the last lecture, we discussed the mechanism for the base-catalyzed dehydrohalogenation reaction, which is an E2 reaction mechanism, which requires the base to take off the proton at the same time that the double bond is forming and the leaving group halogen is leaving. And it's a one-step reaction whose rate depends on both the base and the concentration of alkyl halide. The requirement for the reaction is that it has an antiperiplanar alignment of the proton that's leaving, the carbon-hydrogen bond for the bond breaking and the carbon-halogen bond for the bond breaking, opposite and coplanar or antiperiplanar. And remember that antiperiplanar alignment has consequences on how an elimination could take place, particularly when we discuss and consider rigid systems like these cyclohexane examples that I talked about last time. In some cases, elimination can occur readily in two different ways. In other cases, only a higher energy conformation would allow a hydrogen to be in the proper alignment for elimination. And that antiperiplanar alignment is very important for these kinds of base-catalyzed E2 elimination reactions to occur. So let's move on into Chapter 6. And we've discussed a lot about this elimination, the loss of two groups on adjacent carbons that could be hydrogen and OH in the form of a protonated water, or it can be in terms of a hydrogen and a halogen in the terms of loss of HX, HCl, or HBr. Well, the opposite of this reaction is an addition reaction. It's what we refer to as an electrophilic addition reaction, because it is the addition of a group across a double bond to break the double bond now, and we go from a molecule in which we have sp2 hybridized atoms, and we break those that double bond, form new bonds to the groups in whatever we're adding. Again, something is adding as something in a plus charge state and something as a minus charge state, and that adds across the double bond, and we now have sp3 hybridized situation. Again, an addition reaction is the opposite of an elimination reaction as shown in this top case. Okay, so we should talk about some details of this reaction. There are a number of ways in which addition can be done. So in the beginning of our discussion of elimination chemistry in Chapter 5, we talked about the dehydration of alkanes under high heat conditions to form hydrogen gas and a double bond. Well, this is the opposite of that reaction. It's what we refer to as hydrogenation. That is the addition of hydrogen across a double bond to form an alkane from an alkene. And overall, this is an exothermic process, lower in energy. However, this reaction is actually a very difficult reaction to do because a hydrogen molecule has to be broken. It's very difficult to take a hydrogen molecule and break it into an H plus or an H minus, and as a matter of fact, the chemistry doesn't really work that way. It requires the addition of a catalyst. Although the energetics of the reaction are downhill, there's a very high activation energy barrier because what's required is the need to break apart hydrogen gas, hydrogen molecule, into more reactive species, and then somehow activate that and then allow the addition across the double bond. So a catalyst is something which has no impact in a reaction. It's something that remains unchanged in a reaction, but in some way affects the mechanism or pathway to lower the activation energy overall and increase the rate of a reaction. So for hydrogenation chemistry, this is usually done by some kind of transition metal. You'll often see palladium being used, as I've shown here. Palladium or rhodium is common, platinum, nickel. There are a lot of different transition metals which have the ability to activate or break apart hydrogen-hydrogen bonds. Oftentimes those metals are in the zero oxidation state and supported on some kind of a solid support, these catalysts don't dissolve into the reaction mixtures. So this is what we refer to as heterogeneous reaction mixtures. That is, they're more than one phase. There's the liquid phase that all the organic things are dissolved in, and the hydrogen gas dissolves in the liquid phase, and then the catalyst is a solid in the reaction, usually bound to carbon black, or there's lots of different solid supports. One of the most common ways to do this is to use palladium catalyst bound on a carbon surface, and we often write this as, you'll see it written on reaction arrows as palladium on carbon, or PD over C. And what's happening is it's the palladium atom which is allowing the activation of the hydrogen bond to break the hydrogen bond and form bonds between the palladium and the hydrogens. It's a little more detailed than I've drawn in this schematic, but in a sense the catalyst is activating hydrogen to now add across the pi bond of an alkene. And so if we put in ethylene in this reaction and we've activated the hydrogen, ethylene comes along, hydrogen is delivered and breaking the double bond and forming two new CH bonds, and we form an alkane in the end. This reaction, as I said, could be catalyzed by a lot of different transition metals and can work with a lot of different kinds of alkenes. One of the things that we can use this reaction for is to compare the relative energies of isomers of alkenes. So just like we talked about combustion earlier, and we talked about the heat of combustion of isomers as burning them basically to CO2 in water in the presence of oxygen, and comparing the energy that comes out so we can get an idea about the relative energies of the molecules that we're comparing before they were burned. The same thing we can do through this hydrogenation reaction. And it aligns right with what we know about alkene stability if you take a look at these butene isomers. So we have one butene, we have cis-2-butene and trans-2-butene, and if you hydrogenate all of them, you form butane. So all of these are going to the same product, regardless of which isomer of alkene we start with. And if we measure the heat of hydrogenation, the heat released when we carry out this reaction, what we see is we get more heat out from the 1-butene, 126 kilojoules per mole. If we hydrogenate the cis-2-butene, we get a little less energy, and the trans-2-butene, we get a little less energy out. What that means, of course, is that the trans-2-butene is the most stable, so we get less energy out because it's not at a higher energy to begin with when we convert all of these to the same product. Referred to as heat of hydrogenation. It's another useful tool when we want to compare the properties and energetics of various isomers of alkenes. So heat of hydrogenation helps us to see that. Another aspect of this reaction, which is very important, is that the addition of the hydrogen across a double bond is controlled. That is, it's a stereo-controlled process, what we refer to as a stereospecific process. So we only get the addition of hydrogen to the same side of a double bond if it matters. So for example, we have this cyclohexene substrate now with two substituents on it, and you could add that hydrogen. If you add both hydrogens to the same side, so for example if they both come from the bottom side, you get a cis product, and if they add from opposite sides, you would get a trans product. Well, what's observed is only one product. Only the cis isomer is produced in a transition metal catalyzed hydrogenation. The trans product is not produced. So what that tells us is that in this reaction mechanism, both hydrogens are coming and ending up on the same side of where the double bond was to begin with. So in this case, the ring, it tells us clearly because we would see cis and trans products after hydrogenation. So hydrogenation with a platinum catalyst, the mechanism is not just one atom. So actually, if you take a look at this a little more closely, this describes it a little bit more. We actually have a surface of these metal catalysts. It's multiple atoms involved. So it's actually just not one metal atom. A little more complicated than that. But we have a surface of these, and hydrogen gas gets absorbed on that surface. So you can see I've indicated here a bunch of hydrogens that we've activated. the catalyst doesn't just push those hydrogens onto the alkene. What happens is that the alkene comes close to these metal catalysts as well, and the metal atoms actually first insert on the same side of a carbon-carbon double bond. And so what we have, you might have a metal atom here and a metal atom next to it or further away. Two metal atoms on this surface forming bonds, fixing that on the same side of the ring, and then one of these carbon metal bonds is exchanged for a carbon hydrogen bond, and so that's what you see over here. The CC bond is now replaced with a CH bond, but the other C carbon is still bound to a metal, and so the other hydrogen is also inserted into that to eventually form the product of both hydrogens being added on the same side of the double bond. And that's important. They are what we refer to as a syn addition because the two hydrogens are adding to the same side, okay, to give a cis product. Notice all of the S sounds. Maybe it's a little bit easier mnemonically to think and remember that. Hydrogenation goes with syn addition on the same side to give the cis product. Okay. Well, that being the case, it's also affected because those solid surfaces of metals are very much influenced by how much steric crowding there is around the alkene. So if you take a look at an example like alpha pinene, here we have a ring system where we can clearly see that. So here's the double bond, and the large palladium surface has to approach either from the top or the bottom, and these are no longer symmetric because what we have is this other group which is blocking the top side. And so you can see if we take alpha pinene and carry out the hydrogenation reaction using a nickel catalyst, what we see is that there could be two possible products. Both of these are syn addition of hydrogens, the two hydrogens adding on the bottom side, or the two atoms adding on the top side. So the cis and trans is not with respect to those two hydrogens, so please don't be confused by that. What we're referring to is cis meaning this methyl group and the other alkyl groups, or trans, methyl, and alkyl. That could be a point of confusion in this particular example, so I want to make sure that's very clear. When I use cis pinene and trans pinene, I'm not talking about the hydrogens. In both cases, the hydrogens that added are cis to each other, either on the bottom or the top. Okay, I know that could get confusing, so please try to keep that straight. In any case, what we see in this reaction is that the reaction proceeds selectively to give only the addition of the hydrogens from the bottom side, because that's the more open side. And if you take a look at this more three-dimensional structure here, you can see that this is blocked. So if you have these palladium atoms, or nickel atoms in this case, it's nickel, right? If we have these nickel atoms trying to form bonds with that pi bond here, those p orbitals, it can't do that. But on the bottom here, it's more open, it's less sterically crowded. And so the metal catalysts come from this side, and that's where the hydrogen addition also comes from. So those steric requirements are also very important in this type of process. Okay, well that's hydrogenation, and that's a little different than the opposite of the elimination chemistry that we've been talking a lot about. The elimination of water, dehydration, under acid catalyzed conditions, or the elimination of HX under basic conditions. So if you remember from the last lecture, I talked about the fact that the reverse of this addition reaction, the elimination reaction, is an uphill reaction. Okay? If you go from the right side of this equation to the left side of this equation, this is higher energy, uphill, higher energy, and this is lower energy on the right, the way I've shown it. Okay? So it's downhill actually to do the addition reaction. And so the way we forced the elimination reactions to occur was to use a strong base which would neutralize any strong acid that was present from the halogen halide removal. Okay? However, if you expose a double bond to the presence of a strong mineral acid like HBr, you're going to do what we refer to as electrophilic addition. What do I mean by electrophilic addition? Well, what we have is a double bond. That's where the electron density is. Electron density is at the double bond. As a matter of fact, let me just see if I have a picture of that. I think I have a picture of that next. Yes. So here's the electrostatic potential map for an alkene, and you can see the electron density is located in the pi bond. In this reaction, the reaction first occurs by reaction with a proton. So we have HBr. This is an electrophile. The HBr is an electrophile. The electron density is being donated from the double bond to the hydrogen of the HBr, breaking the double bond, and so this is the nucleophile. Remember, I mentioned those terms some time ago. The nucleophile is the electron-dense species. The electrophile in this first step is the proton coming from HBr. That's why this is referred to as an electrophilic addition, because it's an electrophile adding to the double bond. But keep in note of the directions of our reaction arrows. It's the electron density of the double bond flowing to the electrophile, breaking the HBr bond. This reaction mechanism occurs in the opposite of an E1 mechanism. This addition reaction occurs by protonating the double bond. So I'll put the proton on this carbon on the left, so these electrons moved up to form a bond to the hydrogen, and that left behind a carbon with a plus charge. Okay. Our carbocations, we've talked a lot about carbocations. Electrophilic addition of something plus to a double bond forms a new bond and leaves the other carbon with a carbocation. Again, the opposite of an E1 elimination. And then what can happen is the bromide, which is generated in that first step, adds to that and forms our product. Remember our alcohol substitution under SN1 substitution reaction conditions? This second step is exactly the same as the second step of that process. We form a carbocation, and the bromide or chloride or something like that adds to it. In the first step, it's well, let me be a little more clear. We could do, for example, if I'm using the same generic example, if we protonate an alcohol with HBr, we would end up with this, and in principle this could eliminate water to form a carbocation, and then bromide could add. We showed that substitution chemistry is some of the first reactions we talked about. Okay, so that's electrophilic addition. We will talk a little bit more details. Here is the more detailed mechanism of that I just showed. And not surprising, it has a lot of similarities to the types of reactions we've already been talking about. We have formation of a carbocation, intermediate. The transition state involves the addition of HBr to the CC double bond. So actually this is not really, well, it's a bimolecular reaction. We just call it electrophilic addition. By definition, if we're adding something, it has to require two things coming together. And so it's, again, the electrons flowing to grab the proton of HBr. That's the lowest, the slowest reaction or the highest activation energy. So this first step, as usual, formation of a carbocation, is the rate determining step. And then the second step is addition of bromine or bromide to the double bond, or to the plus charge. And again, overall, this is a net exothermic reaction and produces heat in this process. So it's downhill in energy. Of course, we know that these products have some very specific selectivity associated with it. Actually, the example I just showed on the previous slide, just with ethene is extremely difficult to do. Why? Because the only option when adding a proton to the double bond is to break the double bond and form a carbocation on a primary carbon. Well, if you take a look at this, now we have an unsymmetric double bond. So we have a possibility of forming a carbocation if we protonate this double bond from the electron density in the ring, and if the proton goes on the inner carbon, the number 2 carbon, right, that would form a carbocation. Let me just highlight here. If I put the proton on that carbon, that would leave this carbon empty. That's a primary carbocation. Or these electrons could flow putting the hydrogen on the end carbon. Okay, and I'll just draw it here on the end carbon, leaving the one next to it as the carbocation. Those are two competing pathways. That double bond could break in either direction. But of course they're not done to the same extent. So if you look at the product ratio that's observed, we isolate an 80% yield of the bromine on the secondary carbon. And we see none of 1-bromobutane, the bromine adding to the primary carbon, which means that the carbocation intermediate that would have got there must not have been formed. Obviously, we're comparing the formation of a primary carbocation versus a secondary carbocation, and whether you're trying to do that by protonation of an alcohol and cleaving an O carbon bond, or by addition of H+ to a double bond, the principle is the same. The secondary carbocation is lower in energy, it's more stable, and so it's formed fastest. And as a matter of fact, in this case, the product only results from the formation of the secondary carbocation. Here is some specific examples also which show this as well. Slightly different substitution. In this case, the difference would be if we add the hydrogen on the end carbon, then we would form a tertiary carbocation. Okay, and that's the product we see, the bromine adding to the more substituted carbon. And in this case, and if we did it the other way around, if we added the proton to the middle carbon, right, if I added the proton here, that would be a primary carbocation. So it's primary versus tertiary. Obviously, tertiary is going to win out. Here it's a difference between, if the carbocation is here, it would be a secondary carbocation. If the carbocation is here, it'd be a tertiary carbocation, and that's the one that's formed. So this is a regioselective reaction based on the formation, again, of the most stable carbocation. And I hope you're seeing these recurring themes over and over and over again. We always go with the lowest energy pathway possible when we have a choice. Well, this addition of hydrogen halide to a double bond was something that was studied by a chemist named Markovnikov, Russian chemist. And he came up with a rule based on his observation that when you have an unsymmetrically substituted alkene, it reacts with hydrogen halide. The hydrogen adds to the carbon that has already the greatest number of hydrogens, and the halogens add to the carbon that has the fewer number of hydrogens already existing on it. Now that's kind of a strange way to phrase that, but that was based on the observation of the products they got. Knowing the mechanistic details now, we know that the difference is in the energy of the intermediate carbocation. So if we have two possibilities, such as in this case, it's easier to form the more substituted carbocation. It's higher energy process in this blue case to form the less substituted primary carbocation. So in this first step, the hydrogen is adding to the carbon with the more hydrogens, leaving the carbocation on the carbon with the fewer hydrogens, or the more substituted carbocation. So Markovnikov's description was based on where the hydrogen and proton ended up. Now that we have a good understanding of the mechanism and the formation of carbocation intermediates, it's probably a better way to state Markovnikov's rule as when an unsymmetrically substituted alkene reacts with HX, the protonation occurs to form the more stable carbocation. So the hydrogen ends up on the end, which forms the more stable carbocation, and the carbocation is where the bromine or the chlorine adds to. Okay, now we have an example like this. Here we have an example of, what is this? 3-methyl-1-butene, and under the reaction of HCl, we see the formation of two products. 40% of the product is 2-chloro-3-methylbutene, and 60% of the product is 2-chloro-2-methylbutene. How do we explain that? Well, in this case, what's happening is we have a hydride rearrangement. So the carbocation rearrangements we talked about in the previous chapter are certainly true in this case as well. There are multiple ways in which you could protonate this alkene, right? If you break the double bond, you can put the hydrogen on the left side of the double bond or the right side of the double bond. If we put that hydrogen on the left side of the double bond, I'll put it here, I'll highlight it, that would leave a plus charge on the primary carbon. We know that that's not a competing pathway because that's high in energy. Alternatively, that hydrogen could end up on the end carbon. So I'll just draw the hydrogen is here. Okay, that's the hydrogen that added from HCl, leaving the plus charge now on the secondary carbon, right? And if the chloride that is formed by deprotonation with the double bond adds to that plus charge, you end up with this product which is 40% yield. But in this particular example, what I haven't drawn here, and I'm going to draw this in blue to show you, highlight this, is a hydrogen unwritten which is adjacent here. And in this case, if this shifts over with its pair of electrons, we have the opportunity through a hydride shift or carbocation rearrangement to move the carbocation to a another position. So let me just draw this. I have moved the hydrogen that I've drawn in blue here over to this carbon, and that leaves the plus charge now on a tertiary carbon. And then that's where the chloride adds to give this product, which is the major product. So in this case, it's a clear example of a carbocation formation followed by a hydride shift that results in a different and not predicted set of products. Okay, another aspect of this that we should think about, let's say I have this cyclopentene example and I react this with HCl through this stepwise process of first protonating the double bond with a hydrogen from HCl, with a proton from HCl, and then formation of a carbocation, and then addition of chloride to that carbocation. But notice what happens when we do this. Notice that in the starting material, both of these alkene carbons, okay, are sp2 hybridized. They're flat. That's what I've tried to indicate down here in this sort of side view of the molecule. If you protonate that double bond, now this carbon on the left becomes sp3 hybridized, but the carbon on the right, the carbocation, is still sp2 hybridized. Okay, and so a three-dimensional picture is drawn here below. What you see is this sp3 hybridized carbon now with the hydrogen on the top. The sp2 hybridized carbon has a p orbital which has a lobe above and below the plane. That's still a planar system here. It's flat. The chloride actually could add on either side equally. Although this is a little bit more sterically crowded, so maybe you'll get a little less of this one, where the chlorine is on the same side as the methyl group over here, and a little more of this one. But notice that these are two different stereoisomers, one where the CH3 groups are here on the same side and one where the CH3 groups are on the opposite sides. So you have the cis and the trans. You get about equal amounts. What I'm saying is it's not selective because the carbocation is planar. There's really not much difference in which side that adds to because of the planar nature of that carbocation. So when we talk about stereoselectivity, your book doesn't really cover this too much at this point. I introduce it now so that you're familiar with the concept when we talk about it in more details later on in the semester. Well, another aspect is the opposite of dehydration. That is the addition of water across a double bond, or hydration. The problem is that water itself doesn't react with a double bond because it's not a strong enough acid. It has been shown that you could do the addition of sulfuric acid. It's hard to do the addition of sulfuric acid, but it's possible to do the addition of sulfuric acid across a double bond. Notice what happens here in the mechanism is protonation of the double bond, so the proton adds to the less substituted carbon, leaving the more substituted, more stable plus charge, and then you have HSO3 minus, HSO4 minus as the anion that could add and form a bond. And then this, by the way, this bond is somewhat weak. In the presence of water, you can add water to the sulfur and the hydrogen to this oxygen. You end up with an alcohol. Overall, what we've done is add the equivalent of H plus and OH minus, or H2O, across the double bond. But again, this hydrogen sulfate ion is really a very poor nucleophile. So that nucleophile doesn't add to that plus charge very easily. Actually, forming these is not that easy. If you form a carbocation, however, and you already have water present, then the water could add, because the water, oxygen, is a much better nucleophile. This is the opposite mechanism for acid-catalyzed dehydration, the acid-catalyzed hydration. So if we, let me clear this out and show you an example. If we use 50% aqueous H2SO4, so there's water present, okay, we can go directly from the double bond to the hydrated product, the alcohol, in one step without having to form a sulfate intermediate followed by heating it with water. Okay, so let me just show you, hopefully you can imagine how that mechanism proceeds. Here is the double bond and the H2SO4 aqueous, so there's water present, so please don't forget that. Okay, what do you think the first step is? Well, protonation of the double bond to form an intermediate carbocation. Okay, and this is actually a acid catalyst. Okay, so we generate this plus charge. The hydrogen that we've added from sulfuric acid, I'll highlight it here, ends up on that carbon. Okay, then instead of the sulfate anion, which is a poor nucleophile, adding, since water is already present, water can add to that. So if I just take H2O and add it, okay, we would form this intermediate. Okay, the hydroxonium ion. And then from here, this could lose H plus to form the product, so sulfate can take that back. Those electrons goes to the oxygen, and you regenerate your sulfuric acid catalyst, and you end up with the alcohol as the product. Notice that this is essentially the opposite of elimination. If we go in the opposite direction, right, you have H2SO4 being formed in this step here, this last step. So you protonate the alcohol to get to this carbocation intermediate. You lose water, so water comes off here to form an intermediate carbocation, and then hydrogen is eliminated from the sulfate to go here. So the opposite of this addition of H2O catalyzed by sulfuric acid is the the loss of water under acid catalyzed conditions to form an alkene, a dehydration reaction. The mechanistic steps are the same in the forward direction or the reverse direction. The way we shift this reaction one way or the other is by manipulating the reaction and how it works. So if there's lots of water present under aqueous conditions, we'll get the reaction going to the right. If we don't have much water present or we have concentrated sulfuric acid, what we're going to do is shift this alcohol reaction to the left. That's Le Chatelier's principle that influences the addition of water or the dehydration of water. Okay, how we deal with those differences in those equilibrium. So that's what I wanted to cover in this lecture. We're going to continue talking about different types of additions and different kinds of electrophiles in the next lecture.